Okay, so exam 2 is Friday, right? And the topics are everything up through structures. So no internal loads. Anybody have any homework questions or anything related to the test? Okay. 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 All right. So what was your question? Okay. Okay. Well, let's number these the same. When you did it, did you assume that the joint was part of the lowest numbered member, like I do? Just okay. So, and how did you number it? Did you do 1, 2, 3, 4, 5? Okay, and then which member was it that things were weird on? Okay. Okay, so number 1, you're going to have this. Let me name these two: A, B, C, D, E. Okay, so RA and a couple, I'll call it MA, because that's a fixed joint. And then, do these have weights? They don't, do they? And then here you have the force on 1 by 2. And then here you have the force on 1 by 3 and the force on 1 by 5. Okay, so does that agree with what you had? So then it was just in the calculations where? Yeah. Okay. Okay, and did we choose the same about point? The about point was at A on the right? Okay. Rho, force. On the left for both of us? Okay. Okay, so F13, row vector is 0, force is F13x, F13y, cross is 0, F15, row is 0, force is F15x, F15y. How long is that thing? 1. Okay, so then this is 0.50. The force is F12x, F12y. Cross product is 0.5 F12y. Then RA, row vector is 1, 0. Force is RAX, RAY. Cross product is RAY. And then the couple and that's just MAY. Okay, so that's it for that one. Is that different than I had?
No.
Okay. Any questions about that one? Okay, so now what's the next one you want to go to?
Oh, sorry. It was on that one. So when you found the equations for that one,
Mm-hmm.
when we did the rotational Newton second law,
Yeah.
it didn't have the RA line.
Okay, maybe I just made a mistake on that. But it should be, I mean, so it should say, 0.5 F12Y plus RAY plus MA is equal to 0.
Duality diagram.
Okay.
It was you might have done the cross product wrong for F1.
Okay, so we should have negative F12 at the bottom. And at the top, that's the lowest numbered member at joint C. So we should have forces from both of those. So F2, what is it? 3 and 4. So F2, 3 and F2, 4. And where is the about point for that? At the top? Okay, so F2, 3, 0 row vector, F2, 3x, F2, 3y, 0 moment, F2, 4, 0 row vector, F2, 4x, F2, 4y, 0 cross. And then the height of that is something funky, right, that you have to get from the, so negative F12, what's the height of that piece? 0.182, so this is going to be 0, negative 0.182. And the force is negative F12x, negative F12y. And the cross product is negative 0.182 F12x.
So in equation 6 for the rotational Newton second law. It was positive 0.12.
Okay, I screwed up all over the place. Okay, I was probably watching Dukes of Hazzard or something while I did this. But that's what it should be. By the way, I wouldn't do this on the test. I would keep doing what you're doing, but so there are no weights here, right? And so member 2 and member 3 and member 5 are all 2 force members. You see that? They only have forces at their ends. And so you could treat all of those as cables that also have the ability to have a negative tension, you know, and in a problem like this, and that's like a way you could save some equations and some variables, and you get the same answer. Like you just know that because those are 2 force members, all of those forces have to act along the line between the 2 bodies. That just has to be the case. And what made me think of that is like, you can see right away that our rotational Newton second law says negative 0.182 F12x is equal to 0. So there can't be any x component to this force. And that's why. And there could be x components to these individual forces, but they have to add up to 0. The sum of those 2 has to be 0. Okay, I wouldn't try to mess with, I mean, you'll have time on the test to just do the full thing and whatever, but that is a way you could save some time on problems like this. Any problem where there are no weights given, there's the possibility that you could have some 2 force members that then you could treat with a single variable. Okay, and then is there another one you want to see?
Yeah, the one I was most confused about was the free-body linear
For 3, okay. Okay, so yeah, okay. Well, first of all, since this is not the lowest numbered member at either one of these joints, on member 3, there's only going to be the force from the joint here. There's not going to be the force from 5. So there's going to be a negative F13 on this side. And over here, it's only going to touch member 2 because that's where that joint is. So there'll be a negative F23 there, and that's all. There won't be a force from 4 or a force from 5. Okay, any questions about that? So here there's a negative F13, is that what I said? And then up here there's a negative F23, and that's it. And I guess I'll put the about point here. So rho, force, moment. Well, I guess the length of that has to be 0.5, right? And the horizontal length of it and the height has to be 0.182. So negative F13 has rho vector of 0. The force is negative F13x, negative F13y. Cross product is 0. And then negative F23 has a rho vector of positive 0.5, positive 0.182. The force is negative F23x negative F23Y. And then the cross product is negative 0.5 F23Y plus 0.182 F23X. Okay, Laura, you're just sort of piling on at this point. So the solution is wrong, okay? It's wrong. All right, well, I guess I better redo that solution sometime. By the way, this and this thing, so like I was saying before about the two force members, this is also a two force member. And rotational Newton's second law here says that add these up is equal to 0, which has the effect of saying that those forces have to act along the line of that thing, you know? So again, you could cut down the number of variables if you wanted that way. But I don't think that's a really, like, that's sort of like that's like a cleverness thing. Like it's not really a very useful thing, because if you're writing a computer program that does these calculations, it doesn't care how many variables you have. Any other question? Any other parts of that one that are confusing? So, man, I don't know what happened on that one, and I'm surprised I wasn't aware that that one was screwed up. But it sounds like it's pretty screwed up. Yeah. Any other structures, homework problems anyone wants to see, or questions? Yeah.
Problem 10.
Okay. Oh, I remember which one you're talking about. Okay, so you could do that two different ways. Where is it? So that pulley in the middle, even though I didn't number it, you could make that its own member. And then it would have a fourth, you know, since 2 is the lowest numbered member there, it would have a force on, let's call that pulley P, body P, okay? So there would be a force F2P, and then there would be the two cable forces. So that's one way you could do it. Another way you could do it is, well, as you know, the more rigid bodies you isolate, you know, the more equations and variables you get. So you could also consider that to be connected to body 2 or body 3, you know, just lump it in with those things. And either one of those would be fine. So then, let's see. Okay, so number 10. If you include it on body 2, you'd have the forces down here, and you'd have the forces here, that's, you know, I guess I can go look at what those are in a second. And then you'd have the forces, since that's all one cable going over a pulley, you know that it has to have the same magnitude. So you could write it like that, or you could write it as T and you'd calculate that. If you wrote it as T, you get one more good equation, because if you write it like this, you just have an equation that goes away as basically 0 equals 0, you know. Any questions about that? But when in doubt, you might as well just break it up into its own body, you know. You can, this does work, but if you don't see that, it's not really any harm in making the pulley its own body. Any other questions? Okay, well, let me just go back to that example and finish that, and then that's all I'll do today. So this is back to the example from Monday. Where we had this inclined member. And it has a mass of 50 kilograms, a length of 2 meters. This angle is 40 degrees. This angle is 10 degrees. And we calculated the external loads, and then we went through, used the rotation matrix to come up with, so here's what we came up with to start the internal loads calculation. 223.90, 187.87. And then on the other side, we had 91.27, 187.90. And then we had two components of distributed load. This is the thing that we haven't seen before, and it comes from applying the rotation matrix. So we had a distributed load of 157.644. I'll write that as newtons per meter, so you remember that's distributed. And then we had a downward component of 187.872 newtons per meter. And we have the endpoints, and we don't have anywhere along the length where the distributed load functions change. So we only have to make one cut. And our cut was valid over the whole thing. So we have that force at the left end, 223.90, 187.87. And then at the right side, we have the internal loads. And then at the middle, these are both rectangular distributed loads, so we have 187.872 x, and then pointing to the left, we have 157.644 x. And I think that's where we were at the end of last time. And so now we just have to do the, use Newton's laws. So 223.90, 187.87 plus, I'll put these in one vector. So we have a negative x component of 157.644x and a negative y component of 187.872x. And then plus t negative v is equal to zeros. So t is equal to positive 157.644x minus 223.90. And v is equal to negative 187.872x plus 187.87. This is the first problem that we've seen where the internal tension varies as you move along. That's because of that horizontal component of the distributed load. And then the moment equation, if our about point is at the left, like we always use, the force at the left doesn't do anything. That horizontal component of the distributed load doesn't do anything because it acts through the about point. What's the moment arm for this 187.872x? Well, let me write that out. Yep, exactly. The whole thing has a length of x. It's a rectangular distributed load, so the centroid is in the middle, so this is x over 2. So x over 2 times 187.872x. And is that clockwise or counterclockwise? Clockwise, so negative, and then plus m minus vx is equal to 0. So m is equal to negative 187.872 x squared plus 187.87x plus 93.936x squared. So you can combine the like terms and you get m is equal to negative 93.936x squared plus 187.87x. All the checks that I talked about recently still work. And actually, there's one that we haven't seen before. Okay, so dmdx is negative 187 x plus 187, and that's equal to v. So that one works. Then negative dv dx is negative 187.872. Well, and then the negative of that, so positive 187.872. And that's the downward distributed load. So that one works. And now the endpoint things. So there are horizontal and vertical point forces at both ends. Okay, so we expect tension and shear force to be non-zero at both ends. And we'll look at those in a second. I'll show the graphs of those. But then what about the bending moment at the end points? Are there any point couples at either of those two ends? No, so we expect there to be zero bending moment at both ends. And so let me pull up what those graphs look like. What do you think oh, that's what it is. Okay, so that's what that's what these graphs look like. These numbers are sort of hard to see, but for tension, at the left end, it starts out with a tension of -2 something. It's negative, so that's a compression, okay? And then the compression gets smaller and smaller until the tension starts becoming tension towards the end, okay? And then the shear force, it starts out with a positive shear force, ends up with a negative shear force. It's totally symmetrical. And then the bending moment, just like we thought, the maximum bending moment is in the middle, and it's zero at the two endpoints. What can we say about the risk to this thing? Not too much, because the shear force and the bending moment kind of have opposite stories, you know. If the thing is really susceptible to bending, then the middle is where it would break. If it's really susceptible to shear force, then the ends is where it would break. There are some materials like bone, for example, is really good at resisting compression, but not very good at resisting tension, because when do you ever need that? You know what I mean? And so even though it goes up to a lot of compression here, you might be more worried about it there where it's in tension. But really beyond just, so sometimes you can look at these and all three of those internal loads tell sort of the same story, and you're like, yeah, I'm worried about this at the middle or whatever. But a lot of times you look at it and it's like dependent on what kind of material you have. Is it likely to break in shear force? Is it likely to break in bending? And those are the questions that you can answer with stress and strain analysis. Okay, any questions about that? That's all I want to do today. So test on Friday, and then on Monday, I think we'll go back to the board, and I'll put up a sort of a simple structures problem, and we'll just go all the way, you working through a structures problem, using the rotation matrix, calculate the internal loads. Okay? All right. Bye. let me look. Did you